Good morning and welcome to Wednesday, April 15th. This is AP Statistics. Today we're going to start our optional unit for chi-square analysis. I say optional because for this year, AP has decided not to test on this unit because we have our distance learning and it wouldn't be fair universally. However, if you are to take statistics in college or your career has anything to do with statistical analysis, chi-square testing is actually incredibly important. So this is an optional unit. I'd like you to watch the videos. I'd like you to attend to the material, but the assignments will be optional and will earn you extra credit if you do them correctly. And the shortened unit test at the end will also be optional and will only help your grade if you do well on it. So let's begin. Chi-square testing is essentially a test of variance. Sometimes that's what it's called. What we're really doing is we want to see how well a distribution lives up to expectations. There's three varieties of chi-square analysis. There is goodness of fit testing, there is independence testing, and there is homogeneity testing. The last two are really similar to each other. We'll start off with goodness of fit. It is the simpler variety of test. Here's how it goes. We're going to begin with an example, and here's a pretty common one. We're told that a company produces something with certain expectations. Let's take M&Ms, for instance. You might think perhaps that the color distribution is all the same or maybe even random. It's not. In fact, the Mars company, the one that produces M&Ms, publishes their percent breakdown for each color for every variety of M&M that they produce. So we're going to take the classic M&M, and here's what they report. Now again, this sometimes changes and is based on Production Center also, but this was current as of last year anyway. So we have distribution of the classic colors: brown, red, yellow, green, blue, and orange. Okay. So these are the colors that M&M produces for their classic plain M&Ms. So far, so good. All right, great. I'm going to start off by telling you that this is what we actually should expect because M&M's tells us this is what they do. Mind you, if they didn't tell us that there was a breakdown in their percentages, we could just presume that they'd all be equal percentages. And since I see 6 colors up there, each one would be 0.16 repeating. But that's not the case. They're telling us that there's an expected percent breakdown. So when they make their M&Ms, they're producing a certain percent. Here's what they say. They make 13% brown and 13% red, 14% yellow, 16% green, 20% blue, and 24% orange. Now, I don't know if you ever opened a bag of M&Ms and looked for a particular color, but that's actually the breakdown that M&Ms has been using for their classic M&M. All right, so they're not all equal, obviously. That would be 1/6, and they're not. The one that comes closest to being that percentage was green. There should be a lot more orange in every bag than there are red or brown, but again, there's randomness in every selection as well, so there will be sampling variability. You open a fun size pack of M&Ms, you could find all brown. It's just random selection, and there's a very small sample size there. You open one of those 5-pound, family-friendly bags, you should be more likely to find this breakdown because that's a larger sample size. So let's just say that we observe when we open one of those bags. OBS is observed. Here's what we see. This is going to be a 4-row matrix, by the way, just so you know. Here's what I see when I open my bag of M&Ms, all right? I find, and it's not a 5-pound bag, but it's a regular single serve. We have 18 browns, 20 reds, 26 yellows, 22 green, 34 blue, and 20 orange. Obviously, they're not all the same, but also you might suspect they're not in keeping with the expected percentages. I should see more orange than blue. In my bag, I did not. That does not mean anything's wrong. There could be sampling variability. The test we're going to run will tell us whether or not there is reason to doubt. All right, well, I gave you an expected percent, but that didn't tell you how many I actually expected to see. How many M&Ms did I count just now? Well, if you add up everything in the observation row, you find 140 M&Ms. Reason why that's important right now is because I want to know what I expected to see. I expected 13% to be brown. Well, what's 13% of 140? 18.2. Yes, it is important to retain the decimal point. I know you can't see a decimal point of an M&M, but that's okay. It's what I expected based upon the percentage given. Same thing for red, 18.2, because they also had 13% expected. 14% for yellow is 19.6. 16% for green, that's 22.4. 20% for blue, that's an even 28. And I expected 33.6 orange. It's easy to see that we don't have the exact breakdown I expected. I expected 33.6 orange, I got 20. I expected 28 blue, I got 34. Things aren't perfect. That's called sampling variability. But if they're different enough, if they're off enough, we can say there's cause for concern, and we can reject the null, and all that other good stuff is going to take place here also. All right, now, there's a number I have to find that finishes my matrix, and it is the chi-square number. This is called chi-square analysis. Chi is a Greek letter, looks like a cursive X squared. It's not an X, it's the Greek character chi, C-H-I. How do you find the chi-square value? Well, chi-square is observed minus expected squared divided by expected. O minus E squared over E. It's right there. Each one of those category values, color, has a chi-square value to tell you how different from the expected count it truly is. So it's the difference, observed minus expected. Then you square it, so there's no negative values here. And then you divide it by the expected value. So we'd have 18 minus 18.2, negative 0.2, squared divided by 18.2. That's actually a very small number. My chi-square value for this is 0.0022. That's tiny. It can never be less than 0. It can never be negative. It's a chi-square number, and you divide by the expected count, which can also not be negative. So we cannot get a negative chi-square value. Understand? The lowest chi-square value I can find is the number 0. And that would mean it is exactly what I expected to see. No negatives. For red, 20 minus 18.2 squared divided by 18.2 is 0.178. Same thing for yellow, we get 2.0898. Do the same thing for green, you're going to find 0.0071. Blue is 1.2857. And orange is 5.5048. Please notice something. The more different the observation is from the expectation, the larger the chi-square value is. These are tiny, 0.0022, 0.0071. And I actually got almost exactly what I expected for both of them. I was only off by 0.2 for brown and 0.4 for green. Those are very close to the expected value, within one M&M. However, the more different the values became, this was off by 6, so it's a chi-square of 1.2857. This is off by 6.4, 2.0898. This one's off by obviously a lot, 13.6. And it had a high chi-square score of 5.5048. Each one of them has its own difference from the expected value. Each one of them has its own chi-square value. But what's important is the chi-square total. So you add all those numbers up for the chi-square total. The whole distribution is taken as one. It's holistic. So you add up everything in the chi-square line, and I find 9.0676. Is it high? Is it small? We don't really know just by the raw number. It all depends upon the degrees of freedom, which is the categories minus 1. 6 categories, 5 degrees of freedom. All right, so 5 degrees of freedom. Now, I'm going to have to erase my board for lack of space. So take a look and see. Make sure you've written it down if you're taking notes. We move on to the actual analysis here. I got all my values. Then, of course, I'll also tell you what the conditions should have been in the statements because we need those too, but it works out well this way. So remember that our chi-squared total was 9.0676. Remember our degrees of freedom we said was 5. All right, now, in order to find out how likely or unlikely this distribution was, if everything is as expected, I need a function on my calculator, which is the chi-square CDF. Chi-square CDF, which you'll find in the same place you find normal CDF or TCDF, right, under the second bars menu. It wants 3 inputs. It wants to know your chi-square total, which in this case is 9.0676. If it asks for a lower boundary, that's it. It's always the lower boundary. Your chi-square total is always the lower boundary. There's no negatives, so it begins at the value that is our chi-square total, and it goes up to an infinite bound with 5 degrees of freedom. Chi-square testing is never two-tailed. It's always one-tailed because there's no left tail because there's no negative numbers. See where I'm going with this? Our p-value, therefore, for this distribution is 0.1064. That's your p-value. Now, let's presume I was given a 5% alpha. Even if I wasn't given a 5% alpha, this p-value is slightly larger than even the highest common level, 10%. So I'm going to say it's greater than our alpha. Oh, I didn't give you the statements yet. They're real easy. The null statement for a chi-square goodness of fit test is simply this. It's words. All counts are as expected. Meaning we saw everything we expected to see. And the alternate, very simple, not all counts are as expected. Okay. Please understand, this doesn't mean that everything's wrong. It just means that not all the counts are as expected to the level that we can say it's beyond suspicion. Now, I have my null and my alternate. I know from experience that a p-value greater than alpha means I cannot reject my null, okay? We cannot reject the null, which means all colors are, let's just say, distributed appropriately. Okay? Now, let's again understand what that means. We know that there were differences in certain colors. We understand that. It was obvious. It does not mean that the distribution was wrong. It does not mean anything is wrong with either Mars Company's claim or with the machines that produced the colored M&Ms. All it means is that we had sampling variability. There was some chance variation within our sample that led to this distribution being as we saw. Okay, now of course there are conditions as well. Conditions which should be done at the beginning, but again, this was done by example. So we'll just take care of them now. They're the typical conditions that you'd like to see, usually plus one new one. What are the conditions? Was our data taken from a simple random sample? In this case, we can presume that one bag of M&Ms purchased from the grocery store constitutes a random sample. The 10% rule. I counted 140 M&Ms. Is it logical that there are at least 1,400 M&Ms produced by the factory over all time? Of course. The one that's specific to this, though, is the expected counts are all at least 5. Now, in this case, they were all at least 5. We didn't get any expected counts lower than 5. In fact, our lowest expected count was 18.2. All right. There is also a test on the calculator, which we will review next time. What I'd suggest for an assignment is page 695, just number 16, and we'll review that together next time. Have a nice day.